we are pulled toward the other planets, and our orbit is irregular. Gravity's a funny thing. You can never stop it. So if a planet comes a little closer, it's going to pull you a little further from the sun. Or if there's a planet on the opposite side of the sun, you'll be dragged closer to the sun by that other planet's gravity. Milankovitch measured these things a long, long time ago, and he discovered 3 main irregularities in the solar system. Here they come. Number 1, the shape of our orbit changes. Please look up like this. If you grab a hula hoop and you squeeze it or you extend it, that is called our orbital eccentricity. We get a more ovaline orbit because, every now and then planets are pulling us away. And then every now and then the planets cancel each other out and we get a more round orbit. It goes from this to that and back in 100,000 years. Yes?
So do we pretty much remain like the same distance as the sun then?
No.
Or is it farther and closer?
We move farther and closer within each orbit because we're actually offset. Like you can see up there, that's 1 year the orbit, and then that shape also changes. So every 50,000 years when we're close, we're really close. And every 50,000 years, when we're close, we're a little less close.
So it's like pretty much constant. We're not like moving farther.
You mean like
it's cyclical. So we get further at the closest, then closer at the closest, then back to further. So we're not going to get sucked into the sun anytime soon. It's going to take a long time for that. But yeah, over a very long time, when we talk about billions of years, we are all spiraling into the sun. Everything is. So in about 2.5 billion years, I think we'll get sucked into it. Okay, please look up. The shape of the Earth's orbit changes. So you can imagine, in this year, our planet is probably going to be extra cold because in this year, both the northern and the southern summer are further away from the sun. Neither summer is extra hot. So in those years, you get a colder temperature on average. 50,000 years later, you'll be in this shape. And there, both the northern and southern summer are closer to the sun, so they get a little bit more intensity of light. So they generate a little bit more heat, and so you can see this cycle every 100,000 years. Yes?
So is that first orbit?
Yeah.
Wouldn't another part of the year then be warmer? Like
the spring and fall.
Yeah.
Yeah, but the funny thing is, spring and fall don't really count. Because in spring and fall, the northern and southern hemispheres have roughly the same amount of heating, but the southern hemisphere has a lot more water, more thermal mass, and so what really matters to the planet's overall average temperature is how much heat is gained by the southern hemisphere. More water. You can see in the southern hemisphere is almost all water. And so the summer and winter is what makes a difference. And you can see that this will have a hotter summer winter than this, right?
Yeah.
Milankovitch discovered that the shape of our orbit changes like a squeezed and stretched hula hoop, and that would account for some natural variation in climate. But he discovered other cycles too. For example, this one, it's called variation of the Earth's tilt. The angle of the dangle changes. You may know that our Earth is currently at 23.5 degrees off our orbital plane. And that angle changes every 40,000 years from the steepest extreme, 22.1, to the flattest extreme, 24.5, and then it goes back. It's not like we're falling over. Yeah, exactly. That's why the magnetic declination on a map needs to be adjusted every 40,000 years by a little tiny bit. It's called variation in the tilt. You can see it here. The axis around which we spin stands up a little bit, then falls over a little bit, then stands up a little bit, then falls over a little bit. And again, because that affects how much sun radiation is hitting the southern hemisphere, how directly, that also accounts for another pattern. But please look up. That's on a tighter wave because it's every 40,000, not 100,000. Everybody see what I mean by that? Mm-hmm. Please notice, there's this thing when we talk about wave physics called cancellation and aggregation, or cancellation and amplification. Surfers know this. When you get a peak in one cycle, at the trough of the other, they cancel out. But when you get a peak in one cycle at the peak of another, they add up. So, please look up. Sometimes the coldest of those is canceled out by the hottest in this cycle. But at other times, they add up, making it doubly cold. Yeah?
Where are you right now?
We are triply cold right now.
So that's like helpful to our whole global warming.
No, the fact that we're making it, that's really changed so much.
Right. So we have...
Which makes it down.
Exactly. We have found a way to keep the planet despite the fact that we are on a long-term cooling trend.
But if we were on the hot side right now, then we would be like heating it.
Yeah, I mean, our consequences would conceivably be worse. Again, though, it's not the absolute temperature that makes the big difference. It's the rate of that change. And yeah, you're right. If the planet was heating on its own and then we were adding our heating, it would be heating even faster. So yeah, that would probably be worse. Now, third, there's this thing called axial wobble. You know, when you spin a quarter, when you spin a quarter, it starts to wobble as it slows down. Our Earth is not slowing down, but it wobbles anyway. It was from a meteor strike.
Okay.
So we have another cycle. And again, that affects how much radiation reaches the hemispheres. And so again, because the wobble takes 26,000 years, you get an additional cycle of heating and warming. These are called the astronomical theory of climate change. Milankovich's book by that title was a really big book.
Naomi, can you please microwave this for 3.5 minutes? Thank you. Yes.
So, with feeling all the stars aligned and everything was pointing to the warmer side, would that be pretty bad for our Earth? Or?
No, because that's happened a zillion times. And watch this. We can see now in the year 2013, not only the Milankovitch cycles with great detail. So he was mostly right, but we've adjusted some of his math. And we found a lot of other stuff, too, that Milankovitch could never have known about. Like magnetic changes in the Earth's magnetosphere affecting what? Right. So we've discovered cycles in the Earth's magnetosphere. We've discovered cycles of solar radiation. You guys realize the sun has a heartbeat? I believe it's mysterious, but yeah, it also has a heartburn. And it kicks off these solar flares, and that's cyclical. So look, we take the Milankovitch cycles, we add other things we know, like oscillations in the Earth's magnetosphere, patterns of solar forcing, patterns of solar radiation, and when you add all of those things together, you can basically explain the entire known history of global temperature. All the previous ice ages have relatively simple explanations. It was either an overlap of these, or in a couple of other cases, an astronomical event, like a meteor collision, or a comet that clouds the space between the sun and the Earth. Or, by the way, there have been a couple of internal unusual events, like volcanic eruptions. the wacky thing is, we can explain all the known history of climate change by natural causes, except the last 150 years. Since we've started burning fossil fuels, climate has changed separate from all the natural factors that we know. Milankovitch figured this out in the 1940s. Let me remind you, 1940s Siberia is not exactly the cranking scientific climate you would find in UCLA 2013. Siberia 1940 means really low tech. The guy is basically working by himself in an observatory, and he figured this stuff out. Like you and I, we don't know how he did that. I'm guessing you know, I sure don't. But that doesn't mean he didn't have good science. Now we can verify that his science was shockingly good. We've known for a long time how climate can change naturally. The more we learn about the world and about the solar system, the more details we can explain, but please rest assured, it's not make-believe. It's not like we say, I'm going to just throw out a guess that maybe it's CO2. Quite to the contrary. Just because our public is scientifically illiterate doesn't mean science doesn't exist. Most of you cannot perform brain surgery, just so you know, the Incas did thousands of years ago. Most of you cannot predict the cycling of comets, but just so that we're clear, the Aztecs did thousands of years ago. And even though most of the public does not understand the natural cycles in climate, trust me, other scientists do. And we know for sure that there is no natural way to explain the current rate of climate change. All natural causes that we are aware of don't add up to explain current climate change. All right. I need to set up a demo. And so I want everyone to be my witness. This water is continuous. Look, if I add water over here, that'll fill up because those tubes are open. You can see me do it. Everybody should watch. I'm going to add some water on the right, and the level on the left will change. Okay? So they are contiguous, connected water. Not too shocking, that's good. Next, I'm just going to add some color, but there's no special trick. This is just sweet dye. 1, 2, 3, 4, 5. We'll let that dissolve for a while.
Oh, so sick.
And there goes the rest. Okay? Let's give that a little while. We'll come back to discussing this. But first, little vocab for you. This is number 17. It's called the Ocean Conveyor Belt Current, the OCB current, also known as thermohaline current. Anybody know what thermo and haline means? current. Thermohaline current. What does thermo and haline mean?
Hot.
Thermo means temperature, and haline means hold on. Sounding it out. It doesn't sound anything like it. It is salinity. So temperature and salinity. The ocean conveyor belt is moved by temperature and salinity.